All right, today we're going to dive into a really fascinating idea in physics. We're going to look at a new way of thinking about gravity, one that's presented with some seriously clean, rigorous mathematics.
So, we all know the classic picture of gravity, right? Matter tells space-time how to curve, and that curvature tells matter how to move. It's this beautiful geometric dance that Einstein gave us. But what if that's not the whole story?
What if there's another player in this cosmic game? What if the universe isn't just reacting to mass and energy, but it's also responding to information itself? And specifically, this fundamental drive to make things informationally simpler.
See, this totally reframes the question. Maybe the curvature of the universe isn't just a consequence of what's in it, but it's actually a mechanism for optimizing how you even describe what's in it.
And that right there is the heart of what we're digging into today, chi physics. Now, this isn't about throwing out general relativity, not at all. Think of it as this really elegant, minimal add-on, suggesting that gravity, at least in part, emerges from information trying to find its most compressed form.
So where does an idea like this even come from? Well, it starts by going back to the very foundation of how we write down physical laws, field theory, and realizing something might be missing. Okay, so we all know the standard recipe for a Lagrangian, right? You've got two main parts. There's the kinetic term, that's all about how things move and change. And then you have the potential term, which tells you what states or configurations the system prefers to be in. Standard stuff. But here's the thing. There's this third, supernatural term that we've just never really included, and that is the description length of the state itself. It's algorithmic information content. It's Kolmogorov complexity. Basically, how many bits of information does it take to fully describe the configuration you're looking at?
And that is exactly the gap that Xi physics steps in to fill. It proposes we add just one new element to our physics toolkit to account for this. So let's meet the star of the show. It's a new scalar field, and we call it Xi, or Xi. And what it does is at every single point in spacetime, it gives you a number that represents the local descriptive complexity. Think about it this way. The microstate of a chaotic gas would have a way higher Xi than, say, a perfect orderly crystal, because it just takes way more information to describe. You can literally think of it as a density of information, like bits per cubic meter, an idea that's definitely inspired by things like the Bekenstein bound and holography.
So, how do we put this into our physics? Well, we add a new compression term to the action of the universe. This term basically quantifies the cost of a field's complexity, and the universe, like us, wants to minimize costs. And this term has two parts. The first bit, with the gradient of Xi squared, you can think of that as a roughness penalty. Basically, the universe hates messy, jagged descriptions. It wants things smooth. The second bit, Xi log Xi, well, that's straight out of information theory. It's the continuous version of the classic entropy formula P log P. It's like nature has a built-in preference for states that are simple and highly compressible.
Okay, so we've added a new term to the fundamental action of the universe that says it prefers simplicity. So what? What actually happens? Well, this is where it gets really interesting. You take the full action, you vary it with respect to the metric, you know the drill, and what pops out is a modified Einstein field equation. The geometry of spacetime, G mu nu, is now being sourced not just by the usual stress energy of matter, but also by a whole new term that comes from our information field.
And this new source term? It's the stress energy tensor of the Xi field itself. And the really cool part is it behaves just like any other well-behaved scalar field we already know and love, which means the complexity of a state's description now directly contributes to the curvature of spacetime.
So let's just pause and think about what this means. The big takeaway here is that in physics, what curves spacetime isn't just matter and energy anymore. It's also sourced by gradients in information complexity. Places in the universe that are more complicated to describe literally have a different gravitational pull.
And this gives us this just beautiful, clean physical picture. Picture a spot in the universe that's super complicated, right? A real mess, algorithmically. Xi is going to be huge there. And that high Xi value adds positive curvature, which means gravity pulls things together harder right at that spot, actively encouraging that system to find a simpler, more compressible state. It's like the universe has a built-in mechanism for self-simplification.
Okay, but it gets even cooler when you look at this whole thing through a quantum lens. Let's bring in the path integral and see what happens.
Feynman taught us that a particle explores every single possible path to get from A to B. It's this beautiful, wild idea. Well, Xi physics takes that concept and just runs with it. It suggests that it's not just particles taking all paths, but the universe itself is exploring all possible geometries and all possible information states.
So when you look at the path integral, you're summing over all the possibilities to find out what actually happens. But now, that sum isn't just over every possible shape of spacetime, it's also over every possible configuration of our information field, dxi. And every single one of those possible histories of the universe is weighted by the action, which now includes our new compression term.
What this means is that the universe we actually see, the classical reality that emerges, does so because the paths with the lowest total description cost are the ones that add up, that interfere constructively. Gravity isn't just about energy anymore. It's about the universe trying to tell its own story in the shortest, most efficient way possible. It's an absolutely stunning idea.
Okay, so let's just wrap this all up. That is Xi physics, in a nutshell. It's built on a foundation of one new scalar field, one new term in the action, and one really profound central idea.
And you know what's so compelling about it? How minimal it is. This doesn't require a whole zoo of new, undiscovered particles. It doesn't need speculative extra dimensions. It's just gravity, as we know it, plus the principle of compression.
I mean, the math is just clean. It's elegant. It makes predictions we could actually go out and test, especially in extreme places, like the very early universe, or near a black hole's event horizon, where information density is just maxed out. And you know, as a physicist, there's an aesthetic to it. It just feels right.
Look, this is a totally new way of thinking about the rules of the game. It ties together gravity, thermodynamics, and information theory in this really deep, fundamental way. So, here's the final thought, and really it's a challenge. If this idea sparks something, anything in you, then go build it, go test it, go break it. The universe's shortest story is still being written.